Hi guys, I know it's been a while since I have posted a video, but I've got something special for you today. I made this remote controlled car, which is controlled over Wi-Fi, and as you can see it has 5 ultrasonic sensors, as well as this OLED display that displays the battery status and the distances measured by the ultrasonic sensors, and as well as this Android phone that works as an IP camera. So over here you can see the preview of the camera, and this car also has STM32 F4 series microcontroller, as well as these two logic level shifters that converts the 5-volt logic from the ultrasonic sensors to 3.3 volt logic for STM32. So it converts 5-volt logic to 3.3 volt and vice versa. And I also have over here ESP8266 module that provides me that Wi-Fi connection, and I can control this car over that Wi-Fi module, and as well as two step-down modules that provide me 5 volts and 3.3 volts, and also this really powerful motor driver and this powerful lithium 2-cell battery. So that's it, and let me demonstrate how it works. So let's move on to software and driving around my flat just to show you how it works. So as you can see, I have this Java application that I've made called Robot Controller. Over here, here's the preview of the camera. Here's the battery status, it's quite low, and here's the battery status of the STM32. So let's just drive around my flat just to show you how it works. As you can see, the FPS isn't quite high because that Android phone is quite old, it's Android 5. But if I had used a newer one, it would be much better. So the Android battery is dropping quite a lot. So currently we are in the kitchen, and as you can see, I'm just using 20% of the power at that speed, as you can see over there. And it means that the PWM is set to 20%, so that changes the output power and as well as limits the power of the motor. So I think the battery is going to be dead quite soon. It has only 3%. But then I would like to show you how this car is capable of drifting. So see you in the next cut. So let me show you how this Java application looks like when it is launched. It is just like this, and when you launch an IP camera application, then the Android phone starts to stream the image and the battery status. And when I plug in the battery to the STM32, it's gonna take a while until it's boot and connects to my Wi-Fi router, but eventually you will be able to see the battery status of the STM32 and the distances, and as well this animation will stop and the distances will be displayed. And the range of these bars is set to 2 meters, so it is just from the practical point of view, but those ultrasonic sensors can see up to 4 meters and sometimes even more. But that's it. Just let me place this car down to the floor. And I forgot to show you like what's this driving assistance for. So let's say that you are about to crash to the wall. So when you enable this driving assistance and you will get closer, it will automatically reverse. It will override and it will go back. So that's what it is for. When you approach too close to the wall, it will go back. And if you set the higher power setting, now it is set to 20%. When you set it up, let's say, to the 50%, it's gonna go like crazy back, because for the 20% power setting, it is 20 centimeters of the virtual bumper, and when you set the 50% power, the virtual bumper is set up to 50 centimeters, and it also considers only these 3 front sensors. So when one of these distances is closer than this setting, this speed setting, then it goes back. But now in the next cut, let me show you what this car is capable of. It can quite do some quite good drifts. And I just want to show you one small detail. You can load the same battery status and distances via browser. So when I close this application, you can type in the IP address of the STM32, and it will be loaded like this. And when you reload the page, you can refresh the data. So that's it. Okay, let's start explaining, and let's start explaining the hardware part first. So we are currently at the remote robot repository on my GitHub. So this is what the car looks like, and this is the screenshot of the Java desktop application. So you just control the car with the WASD. You use QWERTY digits to set up the speed or the power of the motor driver, and use the R key to toggle the driving assistance. And over here, here's the wiring diagram. So I've used 2 bidirectional level shifting chips that converts the 5 volt logic to 3.3 volt logic, and I used them for these ultrasonic sensors, as well as for this motor driver board. So I just hooked up this 2-cell lithium battery to the motor driver input and used its output, which is the same as connecting to the battery, but it is reverse polarity protected over here. And here goes the voltage from the battery down to these resistors, so I can read out the voltage of the battery, so I know the percentage of the battery, like how much it is discharged. And another power line goes to these two step-down modules that provide me 5 volts and 3.3 volts. And I use 3.3 volts for this ESP8266 and 5 volts for these ultrasonic sensors, and as well for this shield, and it is only for the input logic. So here are some pull-up resistors, and they need some voltage, like 5 volts, to set up some pins. And I've used those 5 volts also to enable motors, motor 1 and motor 2. So that's basically it about this wiring diagram. It's quite simple. And regarding these ultrasonic sensors, how they work, it has been already covered in my previous tutorial. And if you want to see more details, down here, here's the repository. So here you can find out in details like how you can connect multiple ultrasonic sensors to one STM board and how to set them up. So this is quite detailed. So let's move on. And over here you can see the pinout of the STM32F4 series used for this remote robot car. And I've hard-coded a few things like the credentials for Wi-Fi connection, and you should modify it over here, and also this part, and also in the message handler over here, the same thing. So you just need to modify this ESP server init function, the last line, and one of the last else if statement over here. Here's the login for the credentials for the Wi-Fi. And another thing you need to modify is this IP, which will be different on your router, and this is for the Java desktop application. So it will know like where to send HTTP GET requests. So that's it, and now let's move on to STM32 code. So when it comes to this STM32 code, I have set up the clock frequency up to maximum possible to 100 MHz, and I've used 3 timers. Timer 2, which is set up to 1 second period. Timer 3, it is set up to 20 millisecond period, also with interrupt, and also the timer 4 is set up to 58 microsecond period, also with interrupt. And this timer 3 also launches this ADC conversion. So every 20 milliseconds I convert the ADC, which reads the battery voltage over here. And the voltage divider, which consists of those 2 resistors, it divides the voltage to 1/3. So after converting the ADC to voltage, I multiply it by 3 and I get the voltage that is on the battery. So that's roughly it. And when it comes to these peripherals, I use this SPI2 transmit only master for the OLED display, and this UART1 set up to 115,200 bauts or bits per second for the ESP8266 module. And I've set up this SPI speed to quite quite high bitrate to 12.5 megabits per second. It's quite too high, but I've used quite short cables, but if you use longer ones, you will need to lower down this. So you will need to change the prescaler, let's say, to 32 or to 64, just to have like lower bit rate. Otherwise, you may have some issues. So that's it. And now let's move on to this code part. So let's start with the main function. I just initialize all the peripherals, start the timers, the 1 second one and 20 millisecond one, and also start the PWM, and also I try to set the steering to maximum duty cycle and the motor to 0, the duty cycle of the motor to 0. And then I start the ADC, initialize the OLED display, and display there 3 lines: STM32, ESP8266 and booting. And this screen is displayed there until the whole ESP server init function is finished. And also I enable global interrupt for the UART receiving, and set the steering to neutral position. And I frequently check here in this infinite loop 2 flags, 1 second flag and a message handler flag. So this when this 1 second flag occurs, I measure distances, calculate battery, and update the screen. And this message handler handles the messages received by the ESP8266 module. And I also have this net timeout variable. And when I don't receive a message from ESP8266 and some time counts up, then I stop the motors just not to crash into a wall. So now let's move on to this interrupt C file, and over here, here's the timer 2 with 1 second flag, and I just toggle the LED over there. And over here, here's the 20 millisecond timer, and I count up the timeout if it is not 0, so it is related to the UART1. So let's go there. So technically, when I receive a character, I set the timeout to 1, and I save the character by character into the buffer. And when the buffer is full, it never happened because it never has to. But even if so, if the buffer is full, the last digit the last character is overwritten. And when the buffer index is greater than 5, I just check if there was the end of message. And in previous project I've been checking if there was only like end of line, this line feed character, but this ESP8266 gives me carriage return, line feed, carriage return, and line feed, these 4 characters, and that's the end of the message. So that's the message handler flag, so that's it. And when the end of message doesn't occur, I count up, and if it takes more than more than 40 milliseconds, I set the message handler flag to 1 that calls this message handler function. And I also use this timer for this net timeout. And when the timeout is greater than 50, so if it takes a while not to receive a message or anything, I just stop the motors and try to enable the UART again, because sometimes it happened when I was developing this code that I accidentally disabled the UART interrupt. So this may fix it. And this timer 4 works only when the ultrasonic sensors are trying to measure a distance. So this distance plus it means that the time has passed and 1 centimeter is incremented. And also this trigger time and trigger duration is only for the trigger pulse for the ultrasonic sensor. So that's it. And now let's move on to my library, C file. So over here I have a few global variables, and I've defined here trigger ports, trigger pins, echo ports, and echo pins for ultrasonic sensors, for 5 of them. And over here I have this global variable for battery voltage, which is calculated over here by this ADC conversion capital callback function. And this is called every 20 milliseconds because of this timer 3 function, this timer 3 interrupt that starts the ADC conversion, and after this interrupt handler is finished, it calls this ADC callback function. So, and this is my definition, but it is also defined over here. But as you can see, it is defined as a weak function. That means that when it is defined somewhere else, this will be ignored. So that's it, and I have these other functions around for the statistic enable, statistic disable, and it is for this measure distance function, which was explained in my tutorial for ultrasonic sensors. But technically I disable the statistic, which is launched every 1 millisecond, but I want to keep my measurement as precise as possible. So I disable all the interrupts which are unnecessary, such as UART, statistic, and timer 3. I keep the 1 second interrupt running, because when something happens to these conditions, to ultrasonic sensors, it may get stuck. But when I receive 1 second interrupt, then this 1 second flag will be set to 1, and these infinite while loops will break, and the conversion will be finished, and it will unstuck the problem that sometimes occurred. So that's it. And this measure distance function is called by another function which is called similarly, this measure distances. So this measure distances is called every second, and I just loop via these arrays and try to measure sensors one by one. So that's how I measure the distances. And over here I have a few functions that speak for themselves, like ESP reset, ESP server init. You just need to change credentials over here and also over here, and this function also clears the buffer when the message handler is done. This calculate battery is calculated every second as well, and this update screen function speaks for itself. It displays the battery voltage percentage and also the 5 distances of the ultrasonic sensors. And I already explained this one. This string compare function loops through the two arrays and tries to compare them, and if they match, it returns 1, and if they don't match, it returns 0. And this string contains uses this string compare function, but it returns the position of the string if it is found, and if it is not found, it returns -1. And this message handler is called from this place when the message handler flag is set to 1, and I disable the UART interrupt and try to process what command was received. This is the get command for the HTTP GET request, and when that occurs, I send the data to Java application or to a web browser. And I have a few of these commands for the controlling the robot to go forward, backward, right or left, forward, right, forward, left, backward, right, and backward, left, and this is stop. And this condition, if this occurs, it means that the ESP8266 module failed to connect to my Wi-Fi router, and this will try to reconnect. So over here you also need to put your credentials for the Wi-Fi router. And I already explained this one. And this is called when you are trying to control the car, and it also sends the speed value, and it sets the PWM duty cycle. So that's the parameter. And this halt function is called when the battery is at 0% or below. This speaks for itself. This driving assistance, it works as a virtual bumper, so it measures all the distances, but only 3 front sensors are considered when the car tries not to crash. So only these 3 front sensors, these 3 ones, are considered, and when something is close enough within the proximity, then it will try to go backwards. So this only tells that if one of the distances is smaller than defined, it goes backwards, therefore it won't crash into a wall in theory. So, and this how get tick function, I've tried to modify it. It is also defined somewhere else as a weak function, but sometimes it happened to me that in this UART receive interrupt, I got stuck in this call, in this function, and this timeout never ran out, and I've never received a character, even though this UART interrupt occurred. So this only tries to avoid that situation, and when it occurs, very rarely, it resets the microcontroller. So that's it. I wasn't able to fix the problem, but this was the quickest solution. So that's it. That's how you can remotely control the robot. So before I move on to Android Studio project, I would like to show you that I have this old Android 8 phone, Samsung Galaxy A5, and it's been tested that this IP camera works on this as well. So it's been tested on Android 5 and also on Android 8. So that's it. So now we can move on to Android Studio application. So in this Android Studio project over here, I have this texture into which image view is projected from the camera, and this edit text for the IP address, this set button, and this text view where the IP address is displayed as well as the battery percentage. So I have over here this broadcast receiver for the battery, and I calculate the percentage of the battery. This image handler is launched like every 50 milliseconds and tries to send an image to that Java application on my desktop, and this status handler tries to send the battery percentage also to the application, and it uses this string sender which works as a separate thread. And I've also configured this set button that tries to update the IP address, and this text view that displays the IP address and the battery percentage, and that's basically it. So let me show you this thing first. So this image sender tries to send the image every 50 milliseconds, yeah, like this one, and it tries to use this thread image sender to send the image to server. So I just take the image as a bitmap from the texture view that camera handler uses to project a preview, and I just steal the image from it and tries to convert it to an JPEG, and then I try to send it as an array to the server. So that's how it works. So this is what I tried to send, and over here I just try to send it. So that's how it works. And this string sender tries to send the battery status every 1 second. So that's it. I just send this Android battery and percentage, and I lock the screen orientation to portrait using this line, technically these two lines, because I need the activity. And this button set updates the string, and if it doesn't contain dot as an IP should, it just displays a message like a wrong IP. So that's more or less it, because I've used this camera, this fragment camera 2 basic example from the Google. So this project already existed, but I've only added like my own classes, my own variables. So I've created this class, image sender, string sender, these variables, and you can change the default IP that is loaded when the application is launched. So this is my own, but yours will be different, and it will be defined by default. It will be set by default when the application is launched. So this is technically it. It's not much of modification, but it's been fun to try to work this out, how it should work. So that's all for this Android application project. So lastly, let's explain this JavaFX application, where I have created a few classes. This client sender that is made for sending commands, steering commands for my STM32 board. This is my server that tries to receive messages, and this STM32 status that also tries to send this HTTP GET request, and it tries to get the battery status of the STM32 and the distances. And over here in this variables class, you have to change this IP. It is an IP address of ESP8266 module that will be different on your network, on your router. And the last class is defined down here as camera server that tries to receive the messages, receives the pictures, the JPEG pictures from the Android phone, from the IP camera. So that's it. And this server, this my server, receives the battery status from the Android. So those were the classes, and over here, as you can see, I just use this client sender to send steering commands for STM32. It is defined also, it is mentioned somewhere else as well. I just start a new thread for this STM32 status. So every second I try to receive the distances and the battery percentage from the STM32. And over here, here's the variable, the IP of the ESP8266. So for these two, for remote control and the status, I just need that IP defined. I've defined some labels, like a few of them. This image view camera where the image is projected, and here's the logo of the camera. Over here, here I start the camera server that tries to receive the messages and project them into this image view afterwards. And this Android server that also tries to receive battery status from the Android. So this single port is 7770 and this one is 7771. So that's it, and this progress bar can be changed. It is I've defined 5 of them that display the distance, this progress bar, and their angle is defined mathematically as a sine function. So it looks like a bump, and I wanted to define it like quite easily using a single function. Otherwise, I would have to guess the position and the angle just by hard coding it. Now this slider changes the speed of the car, and its value can be updated with keyboard as well. This is the label for the speed, label for direction, label for status, this checkbox for driving assistance that can be toggled also via key. So when the key is pressed, I can use the W, SAD, and R for the driving assistance, as well as the QWERTY digit numbers to set the power, output power of the car. So that's it, and here's what should happen like when I release those buttons W, SAD, and this timeline is launched every 10 milliseconds indefinitely, and I just try to update the label if there's something received, and I also update the label for the direction. This timeline send tries to send a message every 200 milliseconds, like 5 times a second, and yeah, it is over here, like I try to send data to server based on the buttons pressed. So here I have this boolean flags, and if they were set to true, then I basically set the message how it should look like, and add the line feed at the end and send it out. And over here, when the STM32 status is available, I also try to get the STM32 message to get it, and then I print it and display it in a label. And then I try to process it and update the progress bars based on the distances. And this is the distance range, which is set to 2 meters from the practical point of view, but those ultrasonic sensors can see up to 4 meters. And this is when you close the application, all the threads should be stopped. And here's the update image function that sets the image that was received, and that's basically it. Here's the camera server that tries to receive JPEG images and ends up displaying it ends up in this byte array and later on it is updated, because when I receive quite a lot of bytes, I know that it's been a successful image received, and then I set this update image flag to true, that updates the image in the image view. So this is also called from this place. Every 10 milliseconds it is checked whether or not the image should be updated. So that's basically it. This project was more complex than previous ones, but you can learn from this a lot, and over here you need to just change this IP, your Wi-Fi credentials, and that's it, and you are basically ready to go. So thanks for watching, and see you next time. Bye.